can start. So today we have Lee Ge. He's also from City University, but in New York. And he will talk about pseudo-chirality and its conserved pseudonorm in non-Hermitian photonic systems. So whenever you're ready, Lee, go ahead.
Thank you, Andrea. So I would like actually to give this talk in person, but we know now everything seems to be online. To be honest, we haven't done any grocery shopping since March. I mean, everything depends on delivery. So back to my talk here, you probably see the front page of my talk. So I have three figures here. So the one in the middle is actually a photonic realization of a topological lattice, which is similar to, for example, condensed matter system if you pierce this two-dimensional system with magnetic field. So on the right, you can see some details of this structure. Actually, I took this structure from the website of one of my collaborators. So you see the rings, so the size of those rings is about 5 microns across. And so the cross-section shown on the right is about 200 nanometers for the height and then for the width. So the reason I want to show those structures are, first of all, they are related to pseudo-chirality I'm going to talk about later in this talk. But also, I want to emphasize, or maybe just to tell you that even though the system has been realized by many groups actually nowadays, but its symmetry protection is actually not well understood. I mean, its topological protection is well understood, but the symmetry protection is not. So even though this symmetry protection is not due to pseudo-chirality I'm going to talk about, but it's closely related as we realized in the process. Okay. And on the left-hand side, I'm showing you a schematic of the chiral edge state of such a topological lattice. You probably know that because of, for example, the effective magnetic field, that if you launch a photonic state along the edge of the system, actually will go around the edge without going to the bulk of the system. And if you, for example, have a defect somewhere on the edge, like I show here, I hope you can see my cursor here. So it will simply just go around it. Okay, but the question still remains, for example, if I just give you a snapshot like I have here, can you actually tell which direction the chiral edge state is going? Is it clockwise or is it counterclockwise? So to answer that question, actually, pseudo-chirality can come to the help. Okay, so let me start my talk by showing the usual slides I have. So for those of you who do not know where I come from, New York, and here is a picture showing the Midtown Manhattan. You probably recognize this is the Empire State Building, and our graduate center is right next to it. Typically, I would just end here, but for this time, I saw that you might be interested to know, for example, how are we doing in the pandemic. So here I'm showing you a histogram of the daily confirmed COVID cases. This is not actually for New York City, it's for New York State. New York State is much larger than the city in terms of area, but in terms of population, it's not that different. So in the city, we have roughly 8.6 million people, and for the state, something like 18 million people. Okay. So I hope you can read the numbers here. So in the mid-April, our daily cases are over 6,000 a day. So that's when the New York City was the epicenter of the COVID cases in the United States. But now if you see, we're now in the middle of August, near the end, our daily cases are about 600. So I mean, it's not great, but it's much better than before. So that's a reason my university is actually very cautious about having in-person teaching in the fall. As a matter of fact, all our courses, except for some advanced labs, are going to be taught online. Okay, and even our qualifying exams were actually conducted online. So it was without compromises and, of course, debates. But in the end, we saw that was the best option for now. Okay, so since I'm going to talk about the photonic realizations of this new symmetry, I would like to remind you, or if you haven't seen this before, that in Nature Photonics, there was a special issue devoted to PT symmetry. Okay, two collaborators, Liang Feng from University of Pennsylvania and Rami El-Ghameni from Michigan Tech, and I contributed this invited review on non-Hermitian photonics based on parity-time symmetry and beyond. So the reason, the other reason I want to bring this up is because actually I got a question from social media. So now that's a danger of posting your papers on social media. So someone asked me about this picture shown here on the right. This is actually a very simple system. So we have two couple waveguides, one with gain and one with loss. So that's typical PT dimer picture. So shown here are the real parts and imaginary parts of the effective index of two propagating modes. So these effective indexes are the equivalents of the energy eigenvalues of a Hamiltonian. So we see this familiar inverse bifurcation for the real part and then the bifurcation for the imaginary part when the system reaches the exceptional point. The question I got was actually kind of interesting. At the first glance, it looks legitimate because we know that at the exceptional point, the system is still PD symmetric. So when you look at gain and loss, you would expect that the ratio should be 1. Okay, but if you look at this picture we had in the paper, the ratio is not 1. The ratio is something like 3.4. Okay, so when I got this question, I was actually taken back until I realized that, oh no, so that slash is not actually division, that just means and. So in this picture, loss and gain are always the same. So that's given away by the units over here. If this is a ratio, then there shouldn't be any units. So I guess the student didn't pay attention to the unit when he asked that question. All right, so that was just a little anecdotes. So now let me go on with the main subject of my talk today. So I divided into 4 parts. So for the first part is just a brief overview of the non-Hermitian symmetries we're familiar with now, and also the new one I'm going to talk about. Then I'm going to talk about the conserved quantities in non-Hermitian systems and also the equations of motion. Then that leads to my third subject, that is pseudo-chirality and its implications. So finally, I'll talk about some photonic realizations of this new symmetry and why it helps, and also the new insights it provides. Okay, so now about non-Hermitian symmetries. The first one I'll talk about without surprise is PT symmetry. Right? That's everybody loves, everybody is familiar with. So I just want to point out that it is say standard symmetry defined by a commutation relationship between an operator and a Hamiltonian. Right? So here we know that the operator is anti-linear. Okay, of course it was worked by Carl Bender and others in the 90s. So this is the simplest Hamiltonian we know for 2x2 Hamiltonian. So here the parity is just the sigma x operator from the Pauli matrix. And so on the diagonal elements, we have the gain and loss, depending on your definition of signs. So this one may be gain, or maybe this one might be gain. But for the off-diagonal elements, we have just real value couplings. So in photonics, there are many systems you can use to realize the symmetry. So 2 popular platforms are the coupled waveguides and also the coupled optical microcavities. I won't talk about these since you're already familiar with them. So the next symmetry I'm going to talk about is anti-PD symmetry. Okay, so the difference here I want to point out is defined by an anti-commutation relation between the PD operator and the Hamiltonian. So I myself and Tarich work on this when I was actually a postdoc. So for some people, you might say that, well, anti-PD just a PD symmetry Hamiltonian times I. That picture is only true from the mathematical point of view if, let's say that we don't get into the details of the difference between, say, Hermiticity and self-due, and those tricky questions like whether the metric blows up or not. Okay, just for simple, for example, 2x2 Hamiltonians, so we're safe with that. But from the other point of view, you might think, okay, how do I then realize such a Hamiltonian, right? So if you look at the diagonal elements, it's not gain and loss. Actually, it's detuned oscillators. So for example, if you have 2 coupled waveguides, and those 2 waveguides have to have actually different cross sections in order to have those detunings. And even more, so now we actually require the coupling to be imaginary. So if the couplings are imaginary and Hermitian, for example, if one is Ig, the other one is minus Ig, now there are actually standard ways to realize that, as I will mention a little bit when I come to the topological lattice. But now if you have two imaginary and the same coupling, there's no standard way actually to do this. So that's why people has come up with different schemes. For example, you can using two propagating beam, the hot flying atoms. So the atom can actually change from one channel to the other in this chamber, and then realize this type of Hamiltonian. Yeah. And also, since Avad advertised our work shown here on the right, I won't mention in detail, but just to mention that you can also achieve this Hamiltonian in the synthetic dimension, where the coupling is not between two modes spatially displaced from each other, but rather spectrally displaced from each other. So they're just two modes in the same cavity with different frequencies. Okay, so the third symmetry I want to mention is the particle symmetry or charge conjugation symmetry. So this is actually a well-known symmetry in condensed matter context and also in high energy physics. If you think about that, that's actually the same structure as the anti-PD symmetry. You have anti-linear operator. I'll specify what the C operator is. And this anti-linear operator anti-commutes with our Hamiltonian. Okay. So there has been several groups working on this particular symmetry and its extension non-Hermitian systems, including, for example, myself and a group in Japan, and also Heining Schirmer's group. So the focus here is different from anti-PT, which are really just two coupled, say, channels. Here, the focus is on a more like conventional condensed matter system, where you have two-dimensional lattice or even three-dimensional lattice. So as a result of the particle or charge conjugation symmetry, we have a spectrum that look like this. Okay, if you compare this one to the PT one, you realize there is additional minus sign over here. So what that minus sign means is now the spectrum is actually symmetric about the imaginary axis of the complex energy plane. Okay. So if that's the case, actually I can realize a case just like, for example, the PT unbroken phase where all the energy eigenvalues are real. So now I can actually realize a case where all the energy eigenvalues are imaginary. Okay, so what does that mean? So that means if you look at the real part, imaginary part of your spectrum, so the real part is actually flat. So this is actually the wave number within the first Brillouin zone. So this is just to say that we have a flat band, which has interesting properties, for example, in terms of wave localizations and enhanced Lyman interaction and so on. Okay. For the imaginary part, actually is dispersive. So there is frequency dependence in two of these bands I'm showing here. The other interesting feature I want to point out is if you look at here, if all the energy eigenvalues are on the imaginary axis, so that means we can have actually a zero mode, or actually a bunch of zero modes. So this is similar to the Marana zero modes that has been proposed, for example, in topological computing. So here we might be able to achieve something similar in photonics, even though the topological protection is not as the same as in the Marana zero modes. So another symmetry that has found its way from condensed matter context to non-Hermitian physics is the chiral symmetry or sublattice symmetry. So to understand why I put those two symmetries side by side, I'll just show you first what it means in the Hermitian context. So for example, if you look at this simple lattice here on the left, which is Heineken lattice, you notice there are the field dots and then the open dots. So I'm now going to emphasize them using the colors. So between the purple dots and then the orange dots, together they actually gave rise to this sublattice symmetry, meaning that the system now has two sublattices, the purple one and then the red one. So specifically, if we take the projection operator of those two sublattices, take their difference, then that gives us actually this chiral operator C over here. Okay, so as a result of chiral symmetry, we can have a symmetric spectrum about the origin of the energy reference. In the Hermitian context, this just means that my symmetry, my spectrum is symmetric, but in the non-Hermitian context, this means that we have actually some freedom to set the phase of the eigenvalues in the complex plane. Another interesting thing coming out from the symmetry relation, of course, we can again have zero modes whenever the two subscripts are the same. Okay. And like I mentioned, in the non-Hermitian context, if you want to realize this symmetry, it's actually not as straightforward as having two sublattices. It doesn't work, actually. So the easiest approach is actually use asymmetry coupling that a lot of groups have worked on. Again, there are some references over here. So in terms of experimental realization, last year, C.D. Chan's group in Hong Kong, together, I think with someone in mainland China, realized this waveguide coupled geometry. So basically, you see here is a dark line going through the picture. So that is an optical waveguide, and it's coupled to these bright spots, which are the optical resonators. Okay, so each resonator can actually couple to its neighbor on the right through the waveguide. So that's why the coupling is asymmetric, and then they were able to realize this non-Hermitian version of the chiral symmetry.
Lee, we have a question from Babani Mandal. You want to ask it, Babani, or should I read it out? He's not responding, so I read it out. He wrote in the chat, what is the index mu or nu in E?
Yes, so these are just two different energy eigenvalues. For example, this one you found by solving your system. The first one that's closest to 0. This one is the next one closest to 0. And then when you compare the amplitude, you found them to be the same, but they have the opposite signs. So then that tell you that you have this pair that is governed by this chiral or sublattice symmetry. Okay, so I have to apologize because I'm sharing just part of my screen. I cannot see the question section. I cannot see your faces, so I apologize. I have to rely on Andrea to remind me if there is a question. Okay. So let me go to the next one. The last pair of symmetries I will review are the pseudo-Hermiticity and anti-pseudo-Hermiticity. We are also very familiar with them. And we know that even though they are not given by the typical definition of symmetry, such as in a commutation relation or as an anti-commutation relation, but their spectral signatures are identical to some symmetries we are well aware of. For example, for the pseudo-Hermiticity, we know that it has a spectrum similar to a PT one. And for the anti-pseudo-Hermiticity, you can show that the spectrum has the same signature as the anti-PD Hamiltonian or particle pole Hamiltonian. To see this relations, the easiest way to do this is when, for example, this metric eta is well behaved and also your Hamiltonian is symmetric. So when that's the case, you can show that, I mean, just from here, very easily you show that you have this relation here on the bottom. And of course, you realize that eta plays the same role as the parity in PT symmetry. And likewise, on the right-hand side, if I rewrite this anti-pseudo-Hermiticity, assuming H is symmetric, then I have this additional minus sign telling me that this relation is similar to anti-PT or particle symmetry. Okay, so now after reviewing some of the familiar symmetries we have in non-Hermitian systems, I will introduce a new one, which is the pseudo-chirality that we talk about in this paper that will probably be published online this week. So here I want to point out a few differences between pseudo-chirality and pseudo-Hermiticity or anti-pseudo-Hermiticity. So first of all, on the left-hand side, we don't have the Hermitian conjugate, but rather just the transpose of the Hamiltonian. And also on the right-hand side, we have this additional minus sign. So how do we came up with this name? First of all, by pseudo, we just mean that in the definition of the symmetry, we have a similar transformation, similar to pseudo-Hermiticity. And also, we call it a chirality because if you look at its spectrum of the Hamiltonian, it governs that the spectrum has this signature. So again, you have a pair of eigenvalues that are opposite of each other with regard to the origin of the complex energy point. Okay. So the third property I want to mention is kind of interesting because when we talk about symmetry, we normally say that, hey, the symmetry operator transform one of your eigenstate into another one. Right? But if we have a non-Hermitian system, we know there's difference between the left and right eigenstates. So now if you think about what operator can give you a mapping between the left eigenstate and the right eigenstate. Actually, this operator A that satisfies pseudo-chirality can do that. Okay. So if that's not immediately clear, so let me give you some derivations. So here we have, for example, psi mu as an eigenstate of H with the energy omega mu. Here I'm setting H bar to be 1, so I won't distinguish between frequency and energy. So now simply by, for example, applying a few tricks, we have the relationship on the right. Okay, so H transpose multiplied by A and this eigenstate of H give us the thing on the right. Okay, so now if we compare this to the definition of the left eigenstate of H, or rather the transpose of that, okay, we immediately realize that once you act this operator A according to pseudo-chirality on one eigenstate of your system, then we actually recover one left eigenstate. So here C is a normalization constant that can be defined or find out using the bi-orthogonal relation. So here I say this to be a delta function, indicating that this is away from the exception point. If we are at an exception point, actually there is some freedom of choosing C, depending on the, again, the other symmetries of the problem. Okay. So let's say so now to see why the pseudo-chirality is kind of interesting beyond the property I just mentioned, I want to talk about very briefly about conserved quantities and equations of motion, especially in non-Hermitian systems. So first of all, we know that Noah actually had this great paper about how we relate symmetries of the action of the problem to the constant of motion in classical mechanics. So another way to look at this, or maybe should I say a special case, is to look at the Hamilton's equation of motion using the Poisson bracket. So here H is a dynamic quantity that depends on the position, the momentum, position, and time. So it satisfies this equation where this is the Poisson bracket. So if we want to extract some constant motion or conserved quantity from this equation, that's pretty straightforward, right? We just require that the Poisson bracket vanishes, and also this quantity, dynamic quantity F, has no explicit time dependence. Under those conditions, then we find that F to be a constant motion or conserved quantity. So now in quantum mechanics, of course, the correspondence is the Ehrenfest theorem, which says that if you look at the expectation value of a linear operator A, then it's governed by the commutation relationship between this operator or observable A and Hamiltonian. Take the expectation value plus the second term over here. So now if we want to get a conserved quantity or constant of motion, we just require that A to be commuting with H, and also this operator, this linear observable, does not have explicit time dependence. Okay. These are very straightforward. Okay, but I have to remind you that this requires H to be Hermitian. Okay, so now if we have a non-Hermitian system, by keeping the same definition of the inner product, all we have to do is really just keep H and then its Hermitian conjugate separate. Okay, so now from this relation, if we again want to get a constant of motion, then we just require AH equals H dagger A, and also A to be time independent itself. I mean, this is what actually Ali realized in his 2002 paper, that if H is pseudo-Hermitian, which is given by this relation, then we can have this conserved pseudo-norm or constant of motion. So the next question I want to ask is, are there other tricks we can play in non-Hermitian systems, right? So the answer is yes, but then I have to say that here we have to take a utilitarian point of view, meaning that we're not going to delve into whether this applies to quantum mechanics, whether the absolute phase of the wave function meaning anything. So here I'm just going to apply this to a classical wave equation that looks like the Schrodinger equation. Okay, so this brings to the implication of pseudo-chirality. So now what I'm going to do is I'm going to define a different inner product. So this is just the inner product between two right eigenstates. Okay, T here is a transpose. Here I have a typo here that should be mu and mu. Okay, two different eigenstates. So I should say that this is different actually from the bi-orthogonal inner product that we're familiar with. So there, instead of taking the transpose, we also have to have left eigenstate and then the right eigenstate in the same expression. So when do the two definitions become the same? They become the same when the Hamiltonian is symmetric. Okay, and actually under this condition, the pseudo-chirality that we introduced also become the same as the chirality or sublattice symmetry that I mentioned earlier. Because now, if HT equals H, then that simply means that A and H anti-commute with each other. So to review the really unique and interesting properties of pseudo-Hermiticity, pseudo-chirality. So from this point on, I'm going to focus on Hamiltonians that is actually not symmetric. Okay. So now with this definition of inner product, we can now take a look at what it means for the time dependence of this expectation value, quote unquote expectation value. Okay. It's very easy to see that now on the right-hand side, I have this relation, and here I have a plus sign, which actually is similar to the original Poisson bracket than the commutation relation in the Ehrenfest theorem. Nevertheless, now if we want to have a constant motion, we just assert that AH needs to be equal to minus H transpose times A, and also A to be explicitly time independent. So that means what? That means H is pseudo-chiral, like we defined earlier. So having this in mind, let's take a look at how this relation or constant motion can be helpful in a photonic system. Okay. So here I'll first give you some basic ideas about why we want to focus on this asymmetric Hamiltonian, which then distinguishes pseudo-chirality from chiral symmetry. So this asymmetric Hamiltonian appears, for example, when we have broken time reversal symmetry in the presence of magnetic field or a synthetic gauge field. Okay. And also it happens, for example, when the tunneling between two neighboring sites somehow are asymmetric. Okay. So one simple example for such a system is shown here on the bottom. So here the purple side and then the yellow sides are two, say, waveguides or optical cavities. And then we realize some kind of coupling between them, and then the Hamiltonians are written this way. So B1, B2, B3 are just three complex constants, and the sigmas are the polymatrices, 2x2 polymatrices. So if you do a little bit of algebra, we're going to see that the system has chiral symmetry, so given by this operator over here. So that means this chiral symmetry anti-commute with our Hamiltonian. So it also have actually a pseudo-chiral operator given by the second Pauli matrix. Then we have AH equal to HT times A. I think I missed a minus sign over here. Again, so according to what I just said about the non-Hermitian extension, using this new definition of inner product in non-Hermitian systems, we are going to see that this quote-unquote expectation value of A is a constant motion, but then the quote-unquote expectation value of the chiral operator is not. Okay, so this is very easy to do. We just set up a simulation in two coupled waveguides according to those relations. And then, so shown here are the amplitude of the waves when they propagate from left to right as a function, oh, actually as a function of time, rather. So here shows the expectation value, quote unquote again, of the pseudo-chiral operator and also the chiral operator. So for the pseudo-chiral operator, it's a constant, just as we expected. And for the chiral operator, it's not. Okay? So this just shows you that, yes, indeed, the pseudo-chiral operator can determine new constant motion in our system if we look at the proper operator. The other thing I want to mention is, like I mentioned, so if the system somehow becomes symmetric, then actually whatever chiral symmetry you have in your system now also become a pseudo-chiral symmetry. So now let's take a look at slightly different dimer. So now the coupling between the two waveguides or optical cavities are symmetric, and it's also PT symmetric if we require B1 and B3 to satisfy this condition. So B1 is real and B3 is imaginary. So now if we look at again, the operators, I mean, they're the same as before. Again, I missed a minus sign over here for the pseudo-chiral operator. For the time dependence, both the expectation value of A and pi are now expected to be constant motion, which we again confirm in the simulation. So again, two coupled waveguides or optical magnetic cavities propagating as a function of time or space. And then you're going to see that both of those quantities are constants. There is a difference though. So difference, if you look at the value of the conserved expectation value of A, it's actually 0. And if you remember from the previous one, it's also 0. So that brings us to the question of when actually we can have a 0 versus non-zero expectation values due to the pseudo-chirality. So it turns out that we can have this quantity to be 0 if our pseudo-chiral operator is anti-symmetric. So A transpose equals minus A. Based on this principle, actually, we further look at the physics that determines when the expectation value of A is 0. So to talk about that picture, I will introduce actually a particle and a hole similar to the condensed matter system or high energy physics. So here, let me just remind you that if we have the pseudo-chiral symmetry, then we have a symmetric spectrum about the origin of the complex energy plane. So that means if I have a positive energy or somewhere, for example, in the first quadrant, a particle, I can find a opposite eigenstate of my Hamiltonian, say in the third quadrant. So I will refer to that state as a hole. So they form a pair, and they are related by this operator A. So now let's use this relation to see how does this relation A equal to 0 or the expectation value of A equal to 0 are related to the excitation of this pair of particles and holes. So it turned out that if the Hamiltonian, or rather the pseudo-chiral operator is anti-symmetric, then any arbitrary superposition of the particles and holes will give you a 0, no matter how complicated the system is. So in the previous example I gave you is a 2x2 Hamiltonian, but we also have confirmed this for a much larger system, for example, 100 by 100 size couple lattices. There's no question about that. But if you don't have this very special relation, which is actually the general case, then A, the expectation value of A, is non-zero only if both components of a particle pair are excited. Okay, so for example, if your system has many particles and many holes, you can excite, for example, one particle from one pair and the hole from the other pair. They will not give you actually a finite value of A, the expectation value A. Only when both particle and hole are from the same pair will we actually have a finite non-zero value of the expectation value of A.
Lee, there's a question
yes.
from Ali Mustafazadeh. You want to ask the question, Ali? You need to unmute yourself.
Okay. Do you hear me? So I was wondering, why is that this expectation value that you define is real, or for what operators is it real?
Oh, yes. So for this simple Hamiltonian we talked about earlier, it's real because, let me think. So the general answer is it's not real in general. So that's, if I recall correctly. But for that 2x2 Hamiltonian, it's real because I think related to the choice of the B's that we made. I have to look back into the paper, but that's a great question. Okay, I'll probably come back to that question at the end of the talk.
Okay.
All right, so so what I was going to say is that a special case is, for example, if we have a zero mode given by this pseudo-chiral symmetry, then we can regard it both as a particle and a hole. So even if, for example, just this zero mode excited, then it also gives you a finite value of this expectation value of A. Okay. So next, I'm going to talk about really realistic experimental realization. So this is the same picture I showed you earlier. So you can show that if we want to talk about the two differences between a anti-symmetric pseudo-chiral operator versus a general pseudo-chiral operator, again, I think there's a minus sign missed here. We can look at such a lattice. So let me just show you a few properties of this lattice. So first of all, it's, for example, a square lattice. We have n by n resonators. So those resonators are actually not all the say, rings you see here, actually they're just those ones that are horizontal. Okay, so the vertical ones are actually in charge of coupling the neighboring sides, and they can introduce, for example, different phase to the coupling between them. Okay. And so for each lattice side, due to this phase introduced by those vertical oriented rings, you can actually introduce this magnetic flux or pseudo or synthetic magnetic field to the system. So here I say that phi equals pi over 2, piercing each plaquette. So that plaquette is shown here on the right, on the left. So we actually did a little modification to the system. So we introduced a gain edge on the left, and then we introduced a loss edge on the right. So the introduction of those edges are just to form the pseudo-chiral symmetry. If you don't have such a PT relation, then the symmetry is going to be slightly different, which I will mention briefly in a minute. So it shows here we have different colors and arrows. So when you say different colors, that means we have actually imaginary coupling with opposite signs. Okay, and so if you have, for example, those non-arrowed lines, so the sacred one means it's positive, the gray one means it's negative. So these are actually pretty standard nowadays in photonics. So once you have, for example, the electron beam lithography technique or machine, then you can go ahead and fabricate those in your lab. So like I said, so we have the gain edge and loss edge, and also this system has a zero mode if the number of lattice sides in a row or in a column is an odd number. If it's even number, we don't have this zero mode. So now let me tell you why the system has pseudo-chiral symmetry. So it has pseudo-chiral symmetry because of production rule, which unfortunately I don't think I have time to go into. But basically, we have PT symmetry of the system. As you can see, we have a gain edge and loss edge. So we have this P operator here. And we also have actually a chiral operator given again by the difference between the projection operators onto the two sublattices I mentioned earlier. So now if you take the product of these two, then you will recover a pseudo-chiral operator. Okay. As a consequence of this pseudo-chiral operator, then the spectrum of the system should have certain symmetries, like they are symmetric about the origin of the complex plane I said a few times. So here I actually plotted real axis as the vertical axis and the imaginary axis and the horizontal axis. So for the PT symmetry, then just means that we have up and down symmetry. And for the pseudo-chiral symmetry, we have, for example, this guy is related to this guy due to the pseudo-chiral symmetry. Okay. So if now compare to the Hermitian system, so there we have 4 different bands. So the middle two are actually touching each other in the middle by a Dirac point, and then we have actually 2 band gaps here between the first and second band, and then the third and fourth band. So those bands are actually maintained in the non-Hermitian extension, and we're going to look at one particular mode in the lower band. That's going to be actually a counterclockwise chiral edge mode. I will show you in a minute. And before I do that, I do want to show you that 2 years ago, there were several groups who have done the lasing experiment of such topological lattices. So they have exactly the same lattice, and then they have gain only along the edges. So at that time, people were just saying, okay, this is a non-Hermitian extension, straightforward extension of the condensed matter system. So it has the same symmetry protection as before, which is the chiral symmetry I mentioned. But it turned out it's not the case. So I don't think, at least for the experimental groups, they were not quite clear what is the symmetry protection of the system. So in the course of studying pseudo-chiral symmetry, we realized that actually the symmetry protection is given by anti-pseudo-Hermiticity. Okay, so here show the spectrum of such a system. If we do have, for example, gain along the edges, you see that there's no, let me see, how do I show this? Yeah, there is a symmetry between, the imaginary axis over here, right? This is the imaginary axis. So we have the up-down symmetry, which is actually not PT. I apologize for that. This is not PT symmetry. This is rather due to anti-pseudo-Hermiticity, as we can show. So now finally come back to what does pseudo-chiral symmetry can give us in such a topological system. What I want to show here is, again, for the counterclockwise chiral edge mode I pointed out earlier in the spectrum. So this is how the time evolution look like. Okay, you see that you go around the edges, okay, and then you see that the amplitude actually go down a little bit because this is not exactly Gaussian, so there is some spreading in the spatial dimension. So that's why the amplitude goes down a little bit. So now if we look at what are the conserved quantities in this motion, okay, this is not what I intended to do. Okay, here we have it. So here, if you look at the pseudo-chiral operator A and take the expectation value, then that's the black line over here, okay? The reason here it's 0 is not because now the anti-pseudo operator is anti-symmetric, but rather we just excited the whole of a particle pair, okay? So if instead we look at the energy of the photonic state at the function time, you see they oscillate, so it's not a constant, showing that this is indeed a non-Hermitian system. We have two more lines over here. So the dashed line here is actually for for 0 mode I mentioned earlier. So this is both a particle and a whole, so that's why its expectation value is not 0, it's a finite number. Okay, and for the lower line over here, what it is actually the excitation of both particle and whole, meaning that we have the chiral edge state both in the clockwise direction and also counterclockwise direction. So if we have such a configuration, then again, you can show here there's some beating between those two propagating modes, and then when you do extract its constant motion, then we see it's non-zero, okay, as I mentioned earlier. So that's pretty much all I want to show you for my talk. So there are some technical details I didn't put into the talk. For example, like the choices of parameters when the expectation value of this A operator is real or complex. I'll have to defer you to the preprint we have online for that question. Also, even though this paper is only 4 pages, we have actually a extended supplementary section. So that's, I think, 15 or 20 pages. So there you can find answers to some of the questions you probably have in your mind. But with that, I would like to conclude my talk, and then I'll be happy to take any questions.
Thank you very much, Lee.
Can I ask a question? Yeah, can I ask a question?
Go ahead, Babani.
Yeah, okay. In usual quantum theory, if you multiply the Hamiltonian by a constant number, then almost every physics is same. But your anti-PT symmetric is based on that you are multiplying the Hamiltonian with the negative of imaginary quantity, and how it leads to a new physics.
Oh, first of all, I will to clarify that anti-PT is not really the central part of this talk. I just mentioned that as a broad view of the non-Hermitian symmetries we know or are familiar with. So in terms of physics, there are several differences. So for example, we had an archive paper, I think in 2016, talking about what is driving the, say, the transition across exception point. In PT, you can think of this physics as a classical physics, right? Basically, if you have a gain waveguide and loss waveguide, to couple them with real coupling, then the transition basically just means that whether there is balanced energy flow between the two waveguides or not. But if you have anti-PT, if I remember correctly, in that archive paper, I can send you later. So it's not about the energy balance, but rather it's about the coherence between those waves. So whether, for example, they're in phase or out of phase, that is driving that transaction. So that's one difference. The other difference I sort of mentioned also in the talk, that is, even though the physics might be similar to PT, but in order to realize such a system, you actually rely on completely different physics, right? Like in the realization I mentioned about hot atoms. So there, you can actually realize PT and anti-PT simultaneously, but then you have to look at different time snapshots of your system. So from there, you can show, for example, they have different conservation quantities. The wave function will look like different. For example, there is opposite phase relation between those two channels, whether they're in the PT symmetry phase or in the anti-PT symmetry phase, and so on and so forth. The last difference I would like to mention is because of anti-PT symmetry, which I showed you is very similar to the particle symmetry or the charge conjugation symmetry. So anti-PT can actually give you 0 modes, but PT cannot. So that's a big difference. So with those 0 modes, the photonic community are actively looking for applications, such as, for example, a robust 0 mode laser. So here 0, of course, doesn't mean that the wavelength is infinity, but rather if you have a coupled structure of identical operators or waveguides, then you can achieve robust lasing at the same frequency, which is actually not that easy if you don't have the symmetry, because we know that just like in a crystal, right? So if you have a single atom, you couple different atoms together, you have a band. So now if you want to realize a laser using those coupled oscillators, then you're going to have, for example, a spread of your lasing frequency, which is bad for some applications, for example, for remote sensing and so on. So you want to have a single frequency that's very stable. So for that particular application, you can use anti-PT to help you achieve that goal, but you cannot do that with PT.
Okay, thank you.
More questions?
Yes, I have a short, actually, it's a comment more than a question. Very nice talk. Very nice talk. I think one comment is I don't think you really need to mention Noether theorem. Noether theorem doesn't applicable for continuous. It's only applicable for continuous symmetry, and you have discrete symmetry. You can just remove that part.
Thank you for that comment. So actually, we debate about this, whether to put this into our paper or into the title of our paper. But I think, for example, when people think about symmetry, the first thing that comes in their mind from the symmetry point of view is Noether theorem. That's the reason we mentioned that. But you're right. So it's not actually necessary to this discussion. So just mentioning, for example, the Ehrenfest theorem is sufficient.
That's actually all you need here.
Yes. Yes.
Okay. So I wanted to make a comment.
Philip.
Yes. Okay. I want to make a comment, but I also want to ask Lee a general question at the end of the discussion of his talk, if that's okay. But let me go back to the talk. Has there been any discussion at all in classical mechanics of anti-Poisson brackets?
Oh,
and if so, is there some kind of canonical anti-quantization that you could use that could get you into the results that you have?
That's a good question. We haven't looked into that perspective because, so first of all, classical mechanics is not really one of my favorite subjects even in school. So I haven't really looked into the reference over there, but there might be some connection, like I mentioned. So in our equation of motion defined with this new inner product, we have this plus sign instead of minus sign in our commutation relation, quote unquote commutation relation. So that certainly looks more like the Poisson bracket, like I mentioned, rather than the commutation relation in the Ehrenfest theorem. So there might be some connection, but we have to check.
I think you might find something if you look at a classical Grassmann space.
Okay, so I'll probably ask you for some reference afterwards.
Because the discussion of the dimer case, you were explicitly using the Pauli matrices. And so maybe the analog lies not in a normal classical phase space, but in a classical Grassmann space. Anyway,
I have to be honest, I'm not an expert in that perspective. I would like to learn more from you afterwards.
Okay, you can just get in touch with me. I've spent more time on Grassmann than I should have done.
Thank you.
I have a comment.
Yeah.
Could you bring the definition of what you call chiral symmetry?
Sure, yes. Give me 1 second.
Transpose.
I don't want to disrupt the online screen, so I'm just going to go back slide by slides. Okay, here we go. No, the previous one, I think. Further. Right. All right, here I think I have it. Right, here, yes.
So in this equation, you did not put any restriction on this operator A. The only restriction is that it should have an inverse, right?
Yes, again, so I'm not getting into the details, for example, whether A's will behave or not. As you see in my system, I either have 2x2 systems or 10x10, which is will controlled.
Even if in finite dimensions. So if you don't put any restriction on A, if you take the transpose and use this, then you can find out that this H is going to commute with A inverse A transpose.
So say that again, please.
So if you take the transpose of this equation and use it again, you can show that the Hamilton, this H commutes with A inverse A transpose.
Easy so.
It's easy. So if A inverse A transpose is not, for example, a multiple of identity, then your Hamiltonian, you have to have additional symmetry.
I don't see that actually, because if you take a transpose here, the right-hand side also have a transpose on H.
Yes, yes.
So,
then use
Substitute.
you just substitute this equation inside itself.
So you're saying H has to be commuting with A times A inverse? Is that what you're saying?
A inverse times A transpose.
A inverse times A transpose.
Yes.
And so we're defining that symmetry as a commutation relation.
Yes, yes. It commutes with H.
Okay, so that's something we didn't see. Okay, I have to check and see what other implications that has.
Yes. So
Okay,
when you take A transpose to be you took AT equals to A inverse or something like that?
No, here I don't assume any particular symmetry of A. Only when I talk about, for example, when the expectation of A vanishes universally, that requires A to be anti-symmetric.
Yeah. If it's anti-symmetric, then this operator is just multiple of identity, so you don't get anything new. But otherwise, it is going to commute with H.
I see.
More questions?
Yes, maybe coming back to Philip's question. So thanks for the talk, first of all. So about the anti-Poisson bracket, I see what you mean with Grassmannians, because sort of it's something that, that sort of is related to fermions, all that. But I would have said that the classical analog, it's a symmetric versus an anti-symmetric bracket. And in classical mechanics, you would say the symplectic bracket is the symmetric one, and the anti-symmetric one, and the symmetric one is the metric bracket. And that has been investigated in, like Hamiltonian formulations of dissipation and in thermodynamics and these sort of things. So if you have a metric phase space, then you use the metric to make a symmetric bracket, and that would be like the counterpart of the anti-Poisson bracket. And the symplectic would give you the counterpart of the Poisson bracket. But in context of symmetries or something, I'm not quite sure whether anyone has looked at that at all.
Okay. So I say that comment was actually not intended to me, right? That's to Philip.
Well, I don't know. But it might be interesting to see whether there is anything to do with these.
It's a good comment for everyone.
Yeah. Anyway.
Yeah, so recently we did some work about also regarding, for example, sign change in non-Hermitian system. It's actually, in a sense, it's actually very easy and very straightforward, but I don't think I have seen any reference about that. So we know that the weak rotation transformed the metric of the Minkowski space to the four-dimensional Euclidean space. Right? But you can actually do the same for the Schrödinger equation, right? So you do this, you can probably get the thermal, the heat equation, right? So that people know. But if you do this in a time-independent way, so you can also relate the Schrödinger equation to the Helmholtz equation. So there are actually some fascinating consequences of that. I don't think people have explored before.
More questions?
Can I ask a question?
Yeah, sorry. Andreas, this is Joshua.
Yeah, Joshua, but Saikat has a question before.
Okay, I'll wait.
Okay.
Then I'll wait.
Yeah. My question is, you are talking about pseudo-chirality, right? I was just wondering, is there anything similar to it, but something like pseudo-helicity? Because this chirality is kind of brought about from this, sublattice symmetry. And, in honeycomb lattice, there is also helicity. So
I have to apologize. I couldn't hear the question.
so what I'm saying is that the new thing that is here is pseudo-chirality, right?
Right.
This chirality comes from this sublattice symmetry.
Oh, no. Here, it's different. So in the chiral symmetry case, yes, you have two sublattices, but here it's not required. You don't need to have two sublattices. You can even construct this, for example, using a frustrated lattice where you don't have two sublattices. So that's not required.
Okay. So, I mean, then my question is there something kind of pseudo-helicity? Is it possible?
You have to define what is pseudo-helicity that you mean, because in different contexts, you mean different things.
Okay. Thanks.
Joshua.
Hi, thank you, Andreas. Hi, Lee. Thanks for your nice talk. One comment, follow up to Ali's comment. I think Ali is correct. Indeed, in particle physics, your A would be just the gamma 5 matrix, which should anti-commute with the Hamiltonian, and it squares to 1. It's a symmetric. It has a symmetric Hermitian matrix, and it squares to 1. So it doesn't require additional demands on you, make additional requirements on your Hamiltonian. So that's a follow-up on Ali's comment. And now a question. You mentioned Kawabata et al. At the very beginning. So Kawabata et al. They like to take your non-Hermitian Hamiltonian and make a double matrix, sort of hermitized chiral structure. In the off-diagonal blocks, you have H and H dagger. In the diagonal blocks, you have nothing. So, and from that, you can deduce topological properties of the spectrum. Do you do that as well in your work?
No, I don't actually like that particular approach for several reasons. For example, in their definition of particle hole symmetry in the non-Hermitian context,
yes,
it's actually not really what we call particle symmetry in the condensed matter context. It's really just chiral symmetry. And also when they discuss, for example, in their very long PRX paper, I think published last year, when they talk about the symmetry of the topological insulator laser, they have some very strange assumptions, which it does not actually correspond to what actually happens in the experiment. So my student actually look at those papers, but I haven't actually read them in detail. I just read them on some very superficial levels. Yeah.
Okay, thank you. Thank you very much.
Any more questions?
Hi, Lee, this is Hamid. Thanks for the nice talk. I have a question. I didn't understand your comment about this topological laser paper.
Right.
And the connection between that with your work. Can you explain it again? I'm sorry about that.
Oh, yeah, sure. Let me go to the very end. Again, I have to apologize for this. I have to flip through some 20 slides. So let me just go to the spectrum over here. So for them here on the left is a lattice that we're all familiar with, where they just pump, inject energy or carriers into the edges of this topological lattice. So there, they didn't talk about for them what is the symmetry protection of the system. In private discussion, when asked with others, they say yes, they know, but I never seen any official discussion of that in their papers. So what I realized was, so for their system, actually, the symmetry that gave you this sort of protection, so you still have, for example, separated upper band edge and the lower band edge. This is because you have actually anti-pseudo-Hermiticity. So I don't think that was known before our work here. So in connection to what I talked about, the pseudo-chirality I just mentioned that if you do have anti-pseudo-Hermiticity, and on top of that you have PD symmetry, then your system then will automatically have this pseudo-chiral symmetry, which give you this type of structure. You can actually see that very straightforwardly because, like I said, so if you have anti-pseudo-Hermiticity and then you have some kind of symmetry up and down here, if you have PT, then you have this left and right symmetry. So if you combine them together, then you have this diagonal symmetry, which is a pseudo-chiral symmetry over here. I hope that answers your question.
Yes, but then what it makes me puzzled is that one of the things that people they are talking about the benefit of having this topological edge, as you mentioned, is that the system is robust against the disorder in the coupling in the lattice. But then the simple question, the simple actually answer is that why to even create the bulk in order to have disorder in the bulk and then bother yourself with the edge mode that it is, you know, it will be affected by the bulk. But if you have a, you know, an array of the ring just in 1D, then you don't have the trouble of the bulk. Because
yes, I agree with you. I had actually the same question at the beginning, but then later I was convinced that actually the bulk does play a role, because if you had just a one-dimensional, for example, chain of resonator coupled together like a ring structure, then what happens if you have any defect in this chain, then you're going to have reflections, right? But if you have, for example, bulk in the middle, they actually protect you from the backscattering, at least, for example, for part of your phase space. So I think that's the advantage of having the bulk versus having not the bulk.
But that's it is when you want to have transport. But when you are looking to the laser, I don't see that you are looking to the transport. Laser is
oh yeah, for laser there is still, for example, some difference. For example, if you have a unidirectionally propagating laser like this one, like the one shown here, right? If you have, for example, counterclockwise propagating one versus, for example, you have both directions propagating, then you can have actually a more uniform distribution of the amplitude along the edges. So now if you look at the far field, that will give you a higher intensity. So that's one advantage to have this chiral edge state laser versus, for example, standing low laser.
I see. And then next is that in your system, because the mode they are coming in pairs and they are not associated with the, if I understand correctly, with the same k vector, as you said, the one in the second part half of the space, it talks with the fourth part of the complex plane. Then the structure won't be a single mode. There are two modes that they are living at the same time because of the symmetry, obviously. Is it correct?
So that's from the spectral point of view, right? So for example, here, if I'm looking at this bright green dots over here, yes, of course, there will be, for example, a particle here up here with the opposite energy. And when I excite a system, I do have the freedom of exciting, for example, one of them or both of them, or maybe just the one that is living up here. So depending on how you excite the system and whether they appear to be the same pair of particle and holes, then that determines, for example, whether the expectation value of A is going to be 0 or not. So for example, here in this band, I actually have continuous or semi-continuous edge band that have all chiral characteristics. But if I'm exciting this one over here, but then for example, another one with opposite chirality, but further away from the center of the band, then even if I excited both of them, when I look at the average, or should I say the expectation value of A, then it's going to be 0 because they don't belong to the same particle pair.
Got you. And then the final question is that when you look at the spectrum of the system, let's say the ring resonators that you just plotted, on the modes, you are able to see how, for example, how the system, it has the chirality, or only on the transport you can observe that? How from the mode profile you distinguish if you are you have the chirality or not? From the dynamic here, they show and they claim, but I have never seen that they plot the actual eigenmodes of the system and see how they look like.
So for the Hermitian one, I'm not totally sure. I think you probably can look at the face because still like a plane wave, right? So if you look at the face, you can tell which way it goes. But for a system like this, it's probably very hard if not impossible, to detect the phase on, say, consecutive lattice sites. But I have to thank you for that question, because I sort of advertised that question at the very beginning of my talk, but I forgot to mention that. So for example, for this particular eigenstate, right, this is not actually a propagating mode. So for this particular eigenstate, I can know for sure which direction is propagating, or which sense of direction is going to propagate once we form a Gaussian package. So this is because on the two edges here and here, I have gain here and loss here, right? So if you have a gain, then if the mode passes through the gain, we know it's going to be amplified. When it comes back along the loss edge, it has to be decaying, right? So this tells you that this has to be a clockwise mode. If we have the opposite chirality, then we should have the opposite behavior, right? So along the gain edge, if you propagate along the counterclockwise direction, the amplitude should increase instead of decrease. So this is the signature where we can tell the chirality of the eignode instead of the propagating modes, the direction they're going to propagate. I think that's unique for this non-Hermitian system. You cannot find that in a Hermitian system.
Okay, thank you.
Any more questions?
Well, if not, I have a general question, which other people might care to know the answer. Lee, you discussed that you had given your PhD qualifying exams online.
Yes, I know that's a huge compromise. Yes.
As well, could you tell us how well it worked?
So we actually, typically we have 2 days of qualifying exams for 2 days, 2 sessions, each session is 4 hours. But now we actually break that into 4 sessions. So we have classical mechanics, quantum mechanics, statistical mechanics, and electromagnetism. So each subject is 2 hours. So we don't allow the student to have water breaks. I know it's hard, but that's the best thing we come out with. So as you can see from this picture right here, so some students are actually very clever. So they know that a single camera cannot cover the whole walking space they have. So they actually have multiple cameras, like this student, he has 2. So one is looking at his head, the other one is looking from the side. So from this kind of multiple angle, we know that the student is not cheating. I mean, we don't probably need to do that, but it's just to say double check, just to make sure that everything goes as planned. So in terms of distributing the exams online, we actually just use the message function in Zoom. It's not ideal because there were some students, older students, who didn't even realize that the exams were distributed by the message. So they didn't get the test until 20 minutes later. So we have to give them extra time. So what I did actually in my final of quantum mechanics 2, I just share a document online, same like when I'm sharing the screen that you see here. Some students told me that they can scroll through the document or the test individually. So that's great. So I think that's probably a better way of distributing the exams. So in terms of collecting the answers, we gave them 10 minutes to either scan their answers or take photos of the answer, then send them to a shared Dropbox. And then so one of our secretaries were very nice, and then she just confirmed that they received the submissions and gave them timestamps, and then let the student know that their answers has been collected. So I think with all those procedures, it went pretty well. But I have to say that that's just the first day we have. So this picture is taken this Monday. So we have a second day coming on Friday, tomorrow. So we'll see how it goes.
So basically, you're setting up a side camera, which probably would be a cell phone, so that you can get a picture of the student and you can see them working on their desk.
Yes.
Okay. As regards distributing the exam, what we're using is WebEx, and we're going to put a link in the chat that the students can download the exam. That's how we're going to proceed.
I see.
The other thing is, on the grades that you've got, are they sort of similar to what you're getting in the past?
Actually, my session is coming tomorrow, so I haven't started grading yet. But for the final of my quantum mechanics class, I would say they are similar. So
okay, that's basic. I mean, that's basically what is needed.
Right.
Okay, thank
But I have
you.
to say, probably I do give them slightly easier questions.
Well, we've had to completely adapt the teaching, never mind the exams.
Right, right.
Good.
So for example, one question that showed up here is, I mean, in the middle of March, the student knew that we were going to teach online, right? But for the fourth semester, actually some students were panicked because they don't know how to have their first class. If the instructor haven't, for them, emailed them beforehand to tell them, for example, where to look for the links and which textbooks to take. So, you know, these are just new problems.
Okay, thank you.
Thank you, Lee, for the nice talk and the
Thank you.
teaching hints. Yeah.
Thank you very much.
So I think that's it for today. Yeah. Bye-bye, everybody.
Okay. Okay, bye, everybody.